Now we're going to look at reaction rates, catalysts, energy and chemical reactions, and chemical reactions and how they're driven by entropy. So your reaction rates describes how fast or slow a chemical reaction happens. Some chemical reactions are incredibly slow. Some are so fast that they're spontaneous when the conditions are right. They just automatically start going that way. So in order to have a reaction, the reactants must come together and they've got to be oriented in the right way to react. If you're trying to bring them together and they just don't line up so that electrons can combine, they're going to move apart again and not form anything. They also have to have enough energy to break or form bonds that need to happen when you're doing that chemical reaction. So they've got to come together in the right orientation and with the right kinetic energy, which means energy of movement, enough vibrational energy to break bonds and reform the new ones. This energy can come from the movement, or it can also come from sunlight. It can come from heat. That's why we heat up a lot of things to make a reaction happen. And this energy needed to just start a reaction is called your energy barrier. So for example, I have a wood pile. That wood pile would burn very well, but it needs starting energy to get it to burn, which is great. It doesn't just burst into flames outside my house. It has to have kindling, it has to have newspaper, all the right conditions to get it hot enough to burn and continually burn. Otherwise, it just goes out or doesn't even start. And that's called your activation energy. Once you've put in that activation energy, it can sometimes start a chain reaction. If the reaction was favorable, the first reaction gives out more heat than it takes up, which gives heat for the next one to react, and it just keeps going in chain reaction until you're out of the reactants to react. So what increases the likelihood of a chemical reaction happening? The first is when you have more reactants and products present. If you have a higher concentration, they'll collide more often. The more collisions you have, the more likely they'll collide with the right orientation and the right energy to form products. If you have a higher temperature, you're putting more energy into that. That higher temperature helps the atoms move faster, which means they collide more often with plenty of energy, and so you're more likely to overcome your energy of activation and get your products out. So both those things, higher temperature and more reactants present, favor them. We also have something called catalysts. Catalysts speed up a chemical reaction without being consumed. So the catalyst does this generally by lowering the energy of activation. Sometimes what it will do is it will bring a reactant and product or two reactants together to form a product and hold them there until they are oriented in the right direction, and sometimes they even provide the energy for them to combine. But when they're done, they then release that and they're ready to go on and do the same thing again with another set of reactants. So what they can do then is create a set of reactions that are going along the same pathway or a similar pathway but going much faster. In the human body, most of the reactions that we need done in real time. So we are full of catalysts that speed up the speed of those reactions so that we have a successful reaction taking place. Without those catalysts, most reactions would be too slow to happen at the rate we need them to happen. So industry also uses catalysts because the more they produce of a product in a given time, the more they can sell and make money from. So they often are creating new catalysts to drive whatever reactions they want to speed up. And the human body, when it uses catalysts, they're either proteins or RNA, and they're called enzymes. And they speed up many of our physiological reactions. Reactions use energy, or they produce it. Often the energy is absorbed or given off as heat. So exothermic reactions give off heat to the surroundings, and the products are a lower energy than the reactants. So Exothermic heat exits. These are your heat packs. These are your reactions that give flame. These are the things that would give off your energy. There are also endothermic reactions. Endothermic reactions actually absorb energy from their surroundings. So these are the things that give you cold packs. And when you touch them, they're nice and cold because they're absorbing heat from your hands to do their reaction. The heat of reaction is the quantity of heat produced by a reaction. It's usually in kilojoules or kilocalories for units. So we could ask, are these endothermic or exothermic reactions? If I have 2 sodium and I react them with a molecule of chlorine, I get 2 sodium chloride out and 822 kilojoules of heat. So you'll notice the heat exits, is that going to be endothermic or exothermic? And this is an exothermic reaction. If we take phosphorus pentachloride and add 92.9 kilojoules to the reaction, it will split off one of the chlorines and you'll get phosphorus trichloride out. Now, is that going to be an endothermic or an exothermic? Notice it absorbed energy from the surroundings, so that would make it endothermic. So what's happening to cause this heat or release this heat? Your bonds that you form, the sharing of electrons or the donating and accepting of electrons that take place in chemical reactions, have a certain amount of energy to them. So when we break them, that costs us energy. And when we form them, we get energy out. And the difference between the broken, where we're having to invest energy, and the formed, where we're getting back energy, determines whether we're going to release heat or accept heat. So if there's extra energy released by the bonds formed than the ones we had to break, we get an exothermic reaction. If there is more energy invested to break those bonds than to make them, then we're going to get an endothermic reaction, something that's got to absorb more of their energy from the surroundings in the form of heat or light or something that provides energy. So if we have the energy absorbed minus the energy given off, and you get a positive amount, then you've got an exothermic reaction. The endothermic reaction have more energy absorbed than the energy that is given off when you form the new bonds. So the bond energies are found on page 442 of your book, and if you'd like, you can take the energies absorbed and subtract the energies given off to figure out the bond energies for the overall reactions. So you'll take your amounts there, and keep in mind that it kind of works the opposite of your bank account. So if it's positive, that's energy absorbed. And if it's negative, that's energy given off. So an exothermic reaction is going to be negative overall. And an endothermic is going to be positive. So this is just the opposite of what you're probably used to when it comes to bank accounts and their overall balances. To calculate the energy of the reaction, add up the bonds broken, their values, and multiply them by however many of that bond you have, and then subtract the sum of the bonds formed. So here we have hydrogen and oxygen combining to give us water. When we do that, we have to multiply 2 times the bond formed in hydrogen and 1 times the bond for oxygen. That's a double bond in this case. And then we subtract 4 times the number for water, the bonds in water. And that gives us negative 486 kilojoules per mole. So it's an exothermic reaction. And as it turns out, if you take hydrogen in the presence of oxygen and you add the activation energy, it reacts so violently you hear a sound, and you hear a pop and you see flames. So it's just really violent. And this shows that yes, indeed, it releases energy. Chemical reactions are driven also by something called entropy. Entropy is the dispersal of energy, so the more we disperse energy, the greater the disorder we cause, the more likely a reaction will happen. So exothermic reactions spread energy out to surroundings by releasing heat, so that makes them favorable. Endothermic reactions take energy from the surroundings, but if they create more disorder, then they will still be favorable because they're driven by the disorder instead of by the heat that comes in or out.